Okie doke. All right, so look, what I'm going to be talking about today, those of you that saw the presentation a couple of days ago on the gully mapping work, I'm going to be giving a more expanded version of that. So if you did see that, it's worth sticking around because I'll go into a little bit more detail. Before I get into that, I'm also going to be talking about another project that we've done through the NESP program on gully classification. And so I'm going to start with that before going into the mapping work, because there's a number of sort of preliminary aspects of this work that is important for the mapping work. Now, I just want to highlight that the gully classification work that we did through NESP since we completed that project, I think we completed that in, I remember, it must have been 2019, and we've gone on to do further development on that through the Queensland Water Modelling Network in conjunction with Peter Zun, Sean Dar, Andrew Biggs, Don Malcolm and others. So what I'm going to be presenting sort of incorporates some of that further development as well. So just as a starter, just to provide the context. So I think you're all pretty familiar with the fact that gully erosion is a bit of an issue in the GBR catchments. And we have, and this is the conceptual model that's been developed for the NESP program, the water quality component of the NESP program, just to highlight the connections between the catchment and the reef. And we divide the gullies up into these two sort of fundamental types, the hill slope gullies and the alluvial gullies. Now, as part of the classification work, so this is the most fundamental level of classification, but we obviously go into a little bit more detail than this. Now, just as, again, as some sort of context, so many of you will be familiar with the fact that there's a gully mapping program that is being undertaken by DNRME, led by Sean Dar and co. And this, their goal is to sort of map the entire GBR catchments. And they've been going at this for a number of years now, and it's an amazing bit of work, very dedicated work. And what it's doing is looking at fairly coarse resolution, I guess, at 100 metre sort of pixel scale and just defining things on a presence-absence basis. And on that, from that work, we get the sort of sense that from the sort of map that you see here, that there's gullies everywhere, and it looks a pretty daunting task. And when we extrapolate that even to some of the unmapped areas, and this map's a little bit out of date now. I know there's been a bit more work done since this one, but there's something in the order of 260,000 linear kilometres of gullies coming out of that work. Now, that seems a very, very daunting task when we think, if we have to rehabilitate, you know, even a significant proportion of those gullies, that's a lot of work and expensive. So the trouble is that there's a huge diversity of gully forms out there. I've talked about just the basic differentiation between hill slope and these alluvial gullies. But as you'll see, that some of that existing gully mapping work also includes what we call ephemeral channels, these small sort of features that are not really gullies, but they've also been lumped in with the gully, the mapping work in many instances. So it's quite likely that or it seems likely there's a lot more gullies that have been mapped than really need to be actively managed. And so I guess this is where this, the classification work and then the mapping work comes in. So why do we want to classify gullies? So I guess there's a number of reasons. Firstly, we need to be able to identify appropriate rehab and management match the rehabilitation intensiveness to the type of gully. We also need to improve communication. And one of the things that's become very apparent to me, and this was really brought home to me working with the Landholders Driving Change project in the Bowen, is that when we've had the first meetings about this, it was very clear that different people had different ideas of what gullies were, and it was based on their own experience most of the time. And so often I found that we were sort of talking at cross purposes as to really what we were talking about. And this is not confined to just landholders in the GBR. This is an international problem. We also need to, so then we need to be able to prioritise gullies for rehabilitation. I'm going to talk more about that. And this will help us to build better sediment budget models and also to develop management specific sort of typology. So we can go, so rather than thinking about the gully problem as this sort of generic problem, that there are problems that management issues that can be sort of matched to the appropriate gully type in different landscapes. So a classification. So the rationale for this is that we needed to develop a system that was both technical and functional, so that it was really grounded in firm science, but it could be readily applied by practitioners in the field. It needed to be as comprehensive as possible so we could capture as many forms as possible, but not too broad. So limited number of groups and very focused on the erosional part of the landscape. So those parts of the landscape that are actually really delivering sediment to the stream network and then ultimately to the reef. And then there's obviously a very close relationship with soil type. It needed to be flexible so that it could be used in the field and as applied using remote sensing techniques as well. And also to be able to be applied at high resolution. So based on using LiDAR data at sort of 1 meter resolution. So some of the other considerations, we need to be able to develop particular typologies, and I'll talk about the difference between a typology and a classification. So particular rule sets needed to be sort of hierarchical. We need to have a clear definition of what a gully is, a clear definition of what the independent attributes are and of the scale. And the key aspect being relevant combinations of attributes for different purposes in the typologies. So what's the difference between a typology and a classification? So for classification is where we set out to sort of simplify variables in the landscape that are often very complex and continuously varying, but we need to sort of categorize it, convert it into practical categories that make it more usable and applicable for a broad audience. So we need to define or derive attributes that can help define these categories. And this is not specific to just gully classification. The same sort of differentiation applies to rivers, streams, wetlands, whatever. Then once we have these set of attributes and a classification that we can base off from those attributes, we can then use those in different arrangements to come up with typologies, and these may be for different purposes. At the moment, I'm going to be primarily talking about the classification side of the story, and this is just a sort of conceptual model of sort of shows how attribute classification then feeds into typologies, and then we might use that for different applications, mapping or coming up with different rehabilitation strategies based on those typologies. One of the fundamental things, though, we have to tackle, and this might sound obvious to you, but what actually is a gully? And this is when you go back to look at the literature, it turns out that there is actually no clear definition of what a gully is in the international literature. And so we've actually done a review of this. So we've tried to broaden this out actually just beyond the GBR and beyond Queensland to the international context. And it was very clear that when you go into the literature of when people are writing about describing gullies, it's a complete dog's breakfast. So we perhaps foolishly set out to try and synthesize an objective definition of what a gully is and what it isn't, more particularly. Because if we're going to map gullies, we need to be sure that actually we're mapping what really are gullies, and they're not just small channels and things that don't really fit the conceptual model. And this was the challenge. So we've come up with synthesized, based on the literature. I'm not going to go through this conceptual diagram in detail. This is in the paper that that's currently in review as to what we're talking about when we talk about gullies. But we've used this, and this is a synthesis from the literature, and then we've used this as the basis for our classification. And internationally, it's clear there's a whole range of things that people describe that are as gullies, that some of which we don't think are gullies. And so we've perhaps bravely tried to sort of try and come to terms with this literature and set up a sort of a standard definition. Again, I'm not going to go through this in great detail, but we've come up with this sort of 12-point sort of criteria for what a gully actually is. And I guess one of the key things there is also defining what it isn't. And the first point in our gully classification is that it's not just a stream channel, a small stream channel. And there's been a lot of confusion around this. Fundamentally, what it comes down to, and as defined in this figure, is it's an erosional feature in the landscape, which has an active headscarp that's migrating into unincised part of the landscape in unconsolidated sediments and actively delivering those sediments to the stream network. So the majority of the sediment that is exiting the end of that gully comes from within that gully area, not from above the gully. So it's got to have a dominant, what we call an autochthonous source, so from that particular feature. A small stream channel, by comparison, has sources of sediment that are coming from potentially within the catchment of that. So it's not clear that that it's dominated by the erosion from that channel, that it's integrating a whole range of sources. So that's really the fundamental criteria, and there's a whole range of other things there that I won't go through now in detail, but these are fundamental. And I guess probably the most fundamental thing is that, and there's a huge disparity of definitions of what the scale of the incisional feature is in the literature. Everything from a few tens of centimetres to 30 centimetres and half a metre. Now, the original accepted definition of what a gully is up until pretty much now, and this was first developed in the 1930s in the Dust Bowl era in the US, was that it's a feature in the landscape that is big enough that it can't be ploughed out. Now, that definition still is the overwhelming definition that exists today. So, as you can imagine, with changing, machinery and what can be ploughed out now compared to what could have been ploughed out in the 1940s is a bit different. So we have to make it more robust than that. So we've come up with based on a synthesis of all the literature, that it has to be 0.5 metre deep. And there's a lot of literature that says it can only be 0.3 of a metre deep, but there's a grey zone in there between rills and ephemeral gullies, and we've to get around that, we've come up with this 0.5 metre scarp height differentiation. Okay, so that's the thinking, and this is all integrated into our classification process. The other thing that is very apparent when you actually start to look at these things in the landscape is, particularly in the alluvial gullies, is that there's these two different margins. So defining the margin of the gully is part of the problem, because and it's clear that a lot of gullies that we've observed in the landscape have two margins, and we've described these as a soft margin and a hard margin. The hard margin is the bit that most people would stand on the edge of and go, that's the gully. But when you're mapping these things using remotely sensed LiDAR data, these other features become very important as well. And so we've defined both, and the classification sort of incorporates that. And what we call the soft margin, as shown in this image here, and the hard margin, together we call that the gully shed. I'm going to introduce another term later on that I'll explain what the relationship between that and the gully shed is. But that's an important sort of distinction. Okay, so now getting on to and I'm going to go through this fairly quickly, how we've actually come up with this classification. It's quite technical to go through the process, but as part of this project and the subsequent work that we've done on this through QWMN, we've actually developed a handbook that actually guides you through the whole procedure with lots of examples. I don't have time to go through that all now, but I'm just going to sort of highlight some of the criteria that we're basing it on. It's a distinctive erosional landscape unit. We classify it according to the plan form properties, so that's the shape and the internal geometry of the gullies. The relationship between that gully void and the catchment area to the gully, and that the gully shed and the gully catchment are two different things. So often there's more catchment area beyond that gully shed that I just showed. It's also got to have the hydrological connectedness to the drainage network and continuity, and I'll show you some examples of that in a sec. Then we look at the soil material. So some of these characteristics are based on remotely sensed attributes, and others require field investigation. So there's two levels of classification that are relied upon. Now, some of these things, some of the remotely sensed ones could also be measured in the field, like you could do a survey of the gully boundary, but it's a lot easier to do it using the remotely sensed data. So yeah, soil materials is obviously something that we can get some sense of from remotely sensed data based on things like soil colour. But in terms of really validating what that is, you've got to have field data, because one of the key things about gullies is it's not just the surface soil material that we're concerned about, because those are eroding often through considerable depths. We've got to think about the subsoil properties as well, which you cannot get from normal soils mapping. So the only way to define that is to sample the soils actually in the gully walls, or to drill cores and so on that go to depth. The type and extent of the process. We also look at secondary incisional processes. So often there's multiple phases of erosion within gullies. We also look at the broad climatic regime. And then there's the final one is I guess other sort of logistical considerations for management that comes in later. So here's the sort of broad conceptual model. So we start off with the broad context, climate zones. Then we look at what we call the gully domain. So is it the land, which is really the landscape unit that it's in? Is it alluvial landscape? Is it a hill slope? And we actually divide the hill slope units up into a couple of categories. Then we look at the actual gully form. So this is the plan form or the shape of the gullies, and look at the relationship between the actual gully area and the gully catchment. So that's in that component of it. Then we start getting down into more detail of the actual, what's going on in the gully, the cross-sectional shape of the gully, and the soil materials. So whether they're uniform, they're stratified, and different soil types. And we tend to call these soil materials because oftentimes in these alluvial settings particularly, we're really down at depth beyond the zone of sort of classical soil classification. And then we also look at gully erosion activity. So there's a whole range of attributes that give us an indication of how active the gullies are likely to be based on field observation. So for example, whether you've got very steep walls with blocks falling in, lots of evidence of trees falling in, exposed tree roots, all those sorts of things. So this slide here and the subsequent ones just runs through, this is actually what the classification system looks like. And I'm not going to go through this in detail. I'll just give you a broad overview. But this shows the categories and different levels of the classification process. So at the top, we have the climatic regime. We have the defining the gully scale. So often there's gullies, whole gully systems and gullies within gullies, if you like. So you actually have to define the scale at which you're defining it as the first point. Then we look at the gully domain. So whether it's hill slope, alluvial, or a combination thereof, and that's a fairly common scenario. There's this other category called badlands in the international literature. We don't have too many examples of those in Australia, but there are some. Essentially, these are eroding into weathered bedrock. So they're quite a distinct category. The actual gully forms, then we have the different forms, whether they're linear, dendritic, open, scarp-front. There's another one which we're calling ravine. So we've tried to, we've expanded this classification to incorporate what we see in the international literature. Gully form, catchment area, cross-sectional shape. So different, whether it's V-shaped, U-shaped, trapezoidal, so on. And then the continuity, whether it's fully continuous and connected to the stream network or whether it's discontinuous. So there's different, and we can classify things at different orders. So you don't have to apply things. You can stop at different points if you like, but we've included the obviously the whole framework, but you don't necessarily have to always do it, all the way to it. If you can only do it using remotely sensed data, you can go as far as you can get using remotely sensed data. And there are obviously some attributes that you can only incorporate with field observation, which is not always possible. So we'll have a separate classification just for the soil materials. Another one for what you observe in the field for giving an indication of erosion activity. And ultimately what we're trying to do here using all these field attributes is to tie this back to actual observations of measured erosion rates so that we can come up with proxies for if people observe X, Y, Z erosion activity attributes, we can go, okay, well, it's highly likely that gully falls into the category of a gully that's yielding, somewhere between 100 and 200 tonnes of sediment per hectare, something like that, so that we can, as we build up a database, we can actually make some much more informed decisions about what we see in the field in a quantitative sense. So look, there's another example, different gully classification. So we've run through some examples here. I won't run through that now. Underpinning all of this is a database. So when we collect, whether it's remotely sensed data or field data, this all goes into a database, and then the idea is to build this database up so that we can really start to get much more informed decision making on the different categories. So we can actually then have a numerically driven classification once we build this database up. I'm just going to quickly run you through some examples just to give you a sense of what it is we're talking about. So I've talked about the difference between the hill slope and the alluvial type gullies. Sometimes you have a combination, so it'll start out as an alluvial gully and then it'll head up into the adjacent hill slopes. So that's a sort of a composite class. We'll have simple and complex gullies. So there's some real challenges in mapping and defining these things in the landscape. Some of the channel patterns, we have these more linear forms, more dendritic forms, what we call open, so they're sort of wider than they are, much more open in form. Sometimes these open ones just all coalesce along a river margin, and we call that a Scarp-front. There's some examples. And we have these sort of classic alluvial amphitheatre type gullies. And just a schematic diagram of what we talked about when I talked about the continuity, connectedness with the stream network. And so these are sort of characterised into connected, unconnected, or disconnected. And that's based on some initial work that Sean Dar and co did. All right, so look, that's the classification system. I'll leave that there. Now, if there are any questions on that, I'm happy to address those before I go on to talk about the mapping work.
Thanks, Andrew. It doesn't look like we have any questions yet, so I'll get you to continue.
Oh, yeah. Do I need to stop and start again, or are you seeing? Are you seeing that now?
Yes, I can see 5.10.
Project 5.10. Okay, good. All right. So moving on to talk about the mapping work, and so the gully mapping work obviously builds on some of that work we did in the classification project, applying it in the field in terms of mapping gullies in the landscape. Again, just for sort of context, where as part of this mapping project, we're dealing with we're trying to map all of the gullies in hotspot areas where we have, at this stage, we have LiDAR data. And that area is, gradually increasing. So at the moment, we've applied this mapping over about 5,300 square kilometres in 3 catchments, the Normanby, Triple B and Fitzroy. Just as a bit of context, so many of you will be familiar that we've also been undertaking this work looking at gully rehabilitation. I presented this work the other day. two sites here. This is just context. So these are the sort of sites that we're trying to identify in this mapping work to prioritise for rehabilitation work. So we want to find where these sorts of sites are, and the reason for that is that I presented this the other day as a summary of where we got to with the rehabilitation projects. So both in the Normanby and at Strathalbyn and the Burdekin, in terms of meeting water quality targets. Now, in the Normanby, the site there represents about it's sort of more than this now after subsequent years, but it's up over the sort of 2% of the water quality target for that catchment. So in that particular catchment, we only need to find another 60 odd sites of sort of similar characteristics, or similar sediment yield anyway, to rehabilitate to meet the water quality targets. In the Burdekin, where there's a much higher sediment reduction target, 890,000 tonnes, and just in the triple Bs, about 620,000 tonnes. The work that's been done at Strathalbyn currently, and again, this number's higher than this now because there's another year's worth of monitoring and there's been more rehab done, is up over the 1% mark. So, the number's a bit lower than this now. It's probably in the order of 100. So we just need to find about another 100 sites like Strathalbyn, and that will enable us to meet the water quality targets for that catchment. Now, from the original mapping I showed you of, when I said, the mapping across the whole GBR, it looks pretty daunting. When you boil it down to this, and finding another 100 sites sounds much more doable than just when you just see this map of huge expanses of gullies all over the place. I'm just going to jump straight to one of the key results that's come out of this work, and this is data from the triple B, where based on the mapping work there, we've estimated that the gullies that we've mapped there represent around about 1.5 million tonnes of sediment production per year on average. Now, what it showed, this is the population, it's a very skewed population. And so the mapping there shows that around about 2% of all of the gullies by number are delivering about 30% of the total sediment load, and 6%, 50%. So if the catchment target there is, water quality target is to reduce the sediment yield by 50%. So effectively, and that actually boils down to about 1,300 gullies. Now, that's still sounds daunting, but if they were all like Strathalbyn, the number would be even lower. I'm not sure that there's too many, that there's enough to do to rely on, finding another 100 Strathalbyns, if you like. So this is why we need to map and prioritise, because it's to break the problem down to a much more manageable problem. It's not nearly as daunting as it seems. And I think this is one of the great results that comes out of both the combination of the rehab work and this mapping and prioritisation work. So our goal is to sort of identify that 6% of the gully population that is contributing the 50% of the sediment yield. So I'm just going to run you through now how we go about doing this. So we start out with some LiDAR data, like the image on the left there. And what we want to come up with is a map of those features, and then not just all those features, but ultimately we want to come down to a map of the features that are actually contributing sediment. And not all of these features are contributing sediment in significant amounts. But anyway, so our objective is to efficiently and objectively map gullies over large areas. And as I said, we've applied this now over about 5,300 square k's. So what we start out doing is mapping what we call eroded landscape features, or ELFs. And I'll explain in a sec what an ELF is. But we need to be able to do this at the appropriate scale. And again, and as I pointed out, we're using LiDAR data to map these things. So this is at the appropriate scale to enable us to both define sediment yields and to really map these at a resolution that's useful for management prioritization. So what is an ELF? It's not a small mystical creature. It's actually what we call an eroded landscape feature. And so this is when you do a first pass of the mapping process, this is what you're defining. You're defining essentially these depressions in the landscape, some of which are gullies and a lot of which are not gullies. But what we have to do is do this in an objective way. So we have to map the whole landscape, and the first pass pulls out these things we call ELFs. And here's an example. So the ELF, and those of you that are on the ball will recognise that this is actually a similar figure to what I showed you previously in the classification work to define the difference between a hard margin and a gully soft margin. Now, in this particular case, the ELF is synonymous with the gully shed, but this is not always the case. So there's a lot of these ELFs that actually don't have gullies in them. So the gully shed and gully hard margin part of it these are a subset of these, and we have to map these first and then winnow out the stuff that isn't actually a gully. So we've developed this whole toolbox for doing this, and this is a conceptual model of how this process works. I'm not going to go through it all in detail, but what we do is we start with a digital surface model. We have to divide up the landscape into different categories. So we define 3 different landscape categories. We define alluvial land, hill slopes, and then rugged hill slopes. So we define the hill slopes into these 2 categories. And each of these landscape categories we have to map in a different way. This gets us to the point where we have an ELF, and then we go through a filtering process. So this is what the process looks like. So we firstly, in the landscape, define things that are possible ELFs. And then we go through another process that actually, as indicated in this figure here, defines the actual boundaries of these features. The process, this is in alluvial land, it's a slightly different process in hill slope gullies. So we have to adapt the methodology for different landscape units. Then we go through this filtering process. And this is where we really need to, because I'll show you some examples in a sec. First pass comes up, maps a whole lot of features in the landscape, a whole lot of these ELFs. But we have to winnow that down to what really are gullies and what are things that we might, that are contributing sediment and that we might want to then target rehabilitation on. So there's a whole different range of procedures. It's a sort of multifactorial filtration process. And I'll just run you through some examples of that. So this is one of the criteria in the hill slope categories based on, and the hill slopes can be quite tricky because particularly when you're in steep country, the classification is based on a combination of the terrain roughness and the changes in slope. But if the country's steep already, you know, and also often rough, you can often incorrectly map gullies. So we have to, so it's quite tricky in these sort of rugged parts of the landscape to actually filter out the things that aren't really gullies. So we look at breaks in slope. So this little schematic model here shows the difference between a thing that might be just a steep, bedrock, zero order drainage line or a ravine and a gully. So that's one characteristic. Another characteristic is we look at the bare ground signature. So the assumption is that if it's going to be a gully, and it's going to be an active gully, it will need to have some bare ground in it as well. So then we come up with these. So in this case here, we'll have this shows the ELF boundary and the hard margin boundary. The hard margin boundary is based on the roughness parameters, and which is defined using a range of things based on curvature and concavity, terrain roughness indices, and the standard deviation of the residuals of the roughness. We've combined all these characteristics into this thing called the potential active erosion metric, and this is work that James Daly has developed, and we're finding this is also a very useful parameter for not just helping to define the gullies, but actually to come up with an indirect measure of erosion activity. And I'll just show you how that works. So this is a test data set of 645 gullies where we've got actual measured erosion values based on LiDAR, repeat LiDAR data. And we've compared these against the PAE metric. Now, the great thing about the PAE metric is that it can be applied to a single LiDAR data set. So you don't necessarily have to have repeat data. And what we're finding is that there's a pretty good relationship between the PAE metric and the sediment yield. So we can actually use this based on a single pass of LiDAR to actually come up with a reasonable estimate of the erosion rates. Here's an example that shows derived erosion on the left from repeat LiDAR data and the PAE metric on the right. And so going back to these relationships, so there's different sites, so they're landscape specific as well. So you'll see that some of those relationships have different curves, different slopes. Okay, so just an example of how we apply this mapping. So this is a block in the Fitzroy. So this is the first pass of the mapping. You can see, looks like the whole landscape is covered with these ELFs, eroded landforms. So these are depressions in the landscape. Now we also filter out all stream channels. So these are primarily based in first and second order drainages. So then I'll just show you through the different, what the output looks like after each filtration process. So this is the first filtration. So going back to that's the initial one. This is filtered out based on bare soil and internal roughness. And then the final one incorporates the PAE metric as well. And you can see we come up with a much more limited data set. And so it's these ones that are the ones that are likely to be the ones that we would want to focus on in any sort of management prioritization. Now, just as a comparison, so the image on the left is within that block is our mapped active gullies, if you like. The one on the right is the presence absence mapping. You can see, you know, it's a reasonable representation, but we've filtered it down probably quite a bit more than the presence absence mapping. Just to show you what this looks like in that Fitzroy block. So this is across about 1,200 square kilometres. When you look at it by numbers, it's dominated by the colluvial hill slope gullies in terms of actual numbers of gullies, but the same data in terms of gully area is completely dominated by the alluvial gully type. So again, this is another really important sort of justification for classifying gullies. So if we just go in and we say, okay, we want to apply a sort of a standard gully dimension within a whole subcatchment, you at the very least need to break it down into alluvial and hill slope gullies for it to be useful. I just want to just run you through a couple of the other aspects of the work that we've done as part of this mapping project. So one of the other things that we've done is we've developed a method for across whole sort of subcatchment scale is reconstructing the landscape or reconstructing the prior land surface. So to work out what the total lifetime erosion volume is from a gully, you need to be able to reconstruct what the landscape looked like before it was eroded. So we've come up with an objective method for doing this. And so this is an example from the Bowen. You can see on the right is the sort of present day eroded sort of volume. This here shows the reconstructed land surface. And from that, then we come up with a DM of difference to show what the total lifetime volume is from that particular set of gullies. And we've done this for across whole catchments now. So we can come up with the total lifetime erosion volume of gullies at whole catchment scales, provided we've got the LIDAR data, of course. When we combine that with air photo analysis at individual sites, then we come up with these time series of erosion volume through time. And then you can back extrapolate from that to when the gully was initiated. So this is an example from Belmore in the Bowen catchment, showing that this particular gully system commenced in about 1942. And this is a pretty extensive gully system now. We've done this at a number of sites now throughout the catchments. We've got over 60 sites where we've done this air photo reconstruction. And just for the, in the Bowen catchment, we've been able to define the sort of overall population, based on the overall population of these sites, what the initiation dates were for these gullies. And it looks like there's two populations. So the overall average is around about, they started in about the 1930s, but it looks like there's two sort of population peaks, one in the late 1880s and another in the mid 1940s. So that then, when we combine that with our total lifetime volume, gives us some pretty good bounds on the total sediment yield that's been delivered from gullies at large scales across catchments like the Bowen. I'll just show you too how we've used some of the classification work in the mapping. So as I explained in the classification work, without the field data, you can't apply this to the highest resolution, but we can get it to sort of a reasonable level. So this shows we've been able to define three sort of distinct groups based on just on gully form in the Bowen. So then we can apply that, and then we can, once we've looked at it in terms of the spatial distribution of gully forms, then we can also incorporate different soil colour characteristics. So because in this particular instance, we've got reasonable field data sets, so we can actually validate that and then apply, break that classification down even further, just based on the remotely sensed data. There's some more showing those, that breakdown. And just to run you through how we sort of applying this, so using both the mapping and the classification, we can then come up with sediment yields for gullies across at the catchment scale. So with enough sites, so basically what we have is we've got some sites where we've got repeat LiDAR data, and we use that to train the data set for the whole catchment based on the different gully classes. We get different relationships for each one, and then you can apply that to the whole population to come up with sediment yields across the whole population. And then we can use that data to produce curves like this that allow us to show, you know, which are the gullies that are producing the majority of the sediment. And that's the basis for the prioritisation. So in the prioritisation, as I said, this is the process we need to go through to define that sort of 6% of gullies that are contributing to 50% of the sediment yield. So just to summarise, so we've now applied this mapping across nearly 5,300 square Ks in the Bowen, the Fitzroy and the Laura as part of the Normanby catchment. We divide the landscapes up into these three sort of landscape classes. And then we go through this whole process of mapping the ELFs and then breaking it down into the particular, refining that and filtering that data set to come up with our ultimate data set, which is the actual active gullies. This is a whole toolbox of GIS tools to do this, and based on this, we've produced a large database of gullies, gully metrics across that sort of landscape scale. Obviously, there's going to be a constant feedback as we go out and we ground validate this. There will undoubtedly be a need for sort of further refinement of the method, but we haven't done as much ground validation as we like. We were a bit constrained in this last year in terms of field work, but you know, we're pretty happy with where it's got to. So I'll leave it there. Thank you very much.
Thanks, Andrew. We do have a couple of questions if you're okay to take them. The first one was actually from your original initial presentation. It was from Mick Welsh. She's inquiring as to whether the classification scheme can be or will be made into an app at any point, or if it's able to.
Look, that would be the ideal scenario. So in the work that we've sort of gone on to do with the QWMN, that was certainly the intention to develop it into an app. So I think there's a real need to mesh what we've done here with certainly with the field data collection component with the apps that have been developed for the Reef Trust. I think we could do a lot with that in terms of ensuring consistency with what the classification process is, and there's a lot of metrics that would be collected just as standard part of the site assessment through those Reef Trust apps that could feed into this and then allow us to develop that field classification, if you like, based on an app. So it hasn't been done yet. It's certainly something we would like to do, and I think there is great potential to do that.
Yes, thanks, Andrew. And being able to use that toolbox is something that is a follow-on question from Nick Welsh and Suzanne Long, where they've asked, I guess, is it being used to prioritise any work being done under the GBRF program or Queensland Government, or if you saw any opportunity for it to be used under those?
It is. So it's been applied in the Bowen as part of the LDC project. And we would like to see it, rolled out more broadly. So, I mean, obviously it's there in those blocks that we've got where we've applied it. So that, it's already been sort of used, both, by some of the delivery partners on the ground in those relevant catchments, but there's a need to, roll it out over some larger areas, and the only, key constraints there are the LiDAR data. I mean, it obviously does require LiDAR data sort of resolution to apply it at that scale. There's no reason why it can't be applied. But that's obviously what we would hope would happen. It will be a sort of a toolbox of ARC tools that can be then applied. I mean, I would stress though, it's not a click and play method. It does require some expert overview. Gullies are, as I've sort of, I think, tried to explain, are complex things. And so there are sort of decision points that have to be made through the mapping procedure, where you actually have to apply some different thresholds and parameters at different points, so that so it does require some sort of expert oversight. It's not, you can't just click the whole thing and go spit out the thing at the end. It does require, I can't see it ever quite getting to that point. It requires some decision points, but it's I think as automated as we can get it now.
Right. Well, thank you for
that. Answers your question.
I think so. I think Suzanne's just asking how best could management agencies use the work that you've provided. I think you have explained that to a degree there in your answer, but you've just added a caveat that it's a little bit too complex for it to be a click and see solution toolbox that any agency can just adopt readily. Yeah,
I think in terms of the outputs, we can provide those outputs. Obviously, and this is sort of an ongoing process. It does require, ground validation, I guess so, we've mapped fairly large areas. We've ground validated some of it, but it needs more. We do find it applying. We've tried to apply it in three really sort of different landscapes, and it does. So it's pretty robust, but it does require different, some different parameters in those different landscapes.
Great, thanks, Andrew. And just one other clarification question from Nick Welsh here. How much of reef catchments are covered by LiDAR or potentially covered by LiDAR, and therefore can potentially be mapped using your toolbox?
Not enough at the moment. You might be aware we've just started another project with the Great Barrier Reef Foundation, where we've gained access to the Fugro Roams LiDAR data set across Queensland, which is the LiDAR data set that is flown to survey the power grid across Queensland. That actually covers about 10% of the total area of the GBR catchments. Once that's reprocessed, now it's just in a bunch, it's in linear swaths for most of the time following the power line, so it's not, but it's a sample of the landscape rather than the whole landscape. Other than on the coastal areas where, you know, in high population densities, the whole area is acquired with lidar, but that tends to be the areas that don't have huge numbers of gullies in those more humid coastal areas. So yes, to put a number on it, in the parts of the catchments where most of the gullies are, it'll be less than 5%, I would guess. But I mean, I guess the key thing is that we've now got a good idea of where the major hotspots are, and I think we can very strategically target those areas for lidar acquisition, and then do the mapping at this scale. We don't have to map the whole of the GBR catchments using lidar data to. I mean, we've shown that in that triple B area, we can meet the catchment water quality targets in that 3,500 square kilometre area, because it's the real concentration of active gullies. So yeah, we don't necessarily have to map the whole landscape.